So this session is about scripting and interpreted languages. And the goal of this session is to advocate the use of scripted languages, because historically on the clusters, it's always been compiled languages, either C, C++, or Fortran. And we have sessions tomorrow about C and about Fortran, if I'm not mistaken. These are compiled languages. By contrast, here I will focus on interpreted languages. And the idea is to help you choose the one that you would find most useful. And I'm sure that knowing at least one interpreted language is a nice thing to have in your tool belt. So we will talk about the difference between interpreters and compilers. And the session this afternoon is all about compilers, so you will get a difference. I will talk about 4 languages: Octave, R, Python, and Julia. And there are sessions dedicated to Python and Julia to come. But here it will be a very summary of the introduction. I will talk about graphical user interfaces and a bit about literate programming. And also I will show you additional packages or libraries or modules. They have different names in the different languages, but the ideas are the same, that all those languages offer a way to add more functionalities based on code that was shared by other people. I will give you hints on what to do when it's too slow. And then we will see how we can use several at the same time. So at some point you might find out that Python, for instance, is the best language for you, but you realize that there's an R package that just do exactly what you need. You will see that there are ways to use R packages in Python or Python packages in R and so on. So first, about the difference between a compiler and an interpreter. The compiler, the way it works is that it reads the whole text of your code, and then it transforms it in a code that the CPU can directly execute. And so here are examples: C++, Fortran, I've already cited them, but there's also Java, Go, Rust, Haskell. Those are all compiled languages. By contrast, an interpreter will read each line in the code and call the corresponding functionality in its own code. So I've listed already 4, but Bash, Python, PHP, JavaScript, Ruby, they are all interpreted languages or interpreters. These are the main concepts. But of course, the truth is in between, because many interpreters will actually pre-compile the code. Some compilers compile not to CPU machine, to CPU instruction, but to intermediate language that can be interpreted. So the frontier or the border is fuzzy, but basically the main difference is the compiler will take text and produce executable. The interpreter takes text and reads every line and runs what the lines say. The main feature about compiler is their speed, because they are able to apply powerful code-wise optimization, and they also have practically no runtime overhead, because the code that they produce is run as is. There's no additional infrastructure to run them beside the libraries that you will see. While interpreters, they allow easy code introspection, because since they read each line by line, you can do what the interpreter does. You can inspect the objects more easily than with a compiler. And most of the time, they also offer high-level language constructs, because they are much more flexible in terms of objects or data types. You can play with higher-level constructs or objects than you can typically do in a compiled language. So basically, the interpreted languages are easier to learn because many implementation details are hidden. You don't need to manage the memory. You know that if you write a C code, you will need to allocate memory to store your variables. In all the interpreted languages, this is done for you automatically. by the interpreter. They are easier to exchange or reuse because a Python code can run on any operating system as long as there is a Python interpreter on that. And also they allow for faster development because they lead to a higher level programming, and they they have a lot of built-in support for mundane tasks. So they can handle not numbers, infinite values, they can handle files, dates. If you work with time series, you can, the dates by themselves are most of the time an integral part of the program. It's not an external library that you need to use to play with the dates. So here I will focus on Octave, Python, R, and Julia. And you might wonder why those four, but actually because they are all very much used in scientific applications. R is very strong for statistics. Octave is strong for engineering. Python actually is a generic language, but with the addition of the NumPy and SciPy package, it becomes a fully scientific language, and it's very strong and very used in data science. And Julia is a much younger language, where the promise was to take everything that was good in all the above, R, Octave, and Python, and put it in a single language. So this is what they promised. They are all free, and free in the sense that they are open source and you don't have to pay to use them. They are all performance oriented, and most of them started as wrappers for Fortran code. So Fortran code can be very efficient, but not easy to write. And all of them actually are Octave and Python and NumPy were all projects that started with the objective of having people, either students or a researcher, have access to Fortran code without the need to write actual Fortran code. By contrast, if you know about Ruby or Perl, they're also used in scientific context, but in more smaller communities, mainly bioinformatics. If you know about PHP or Bash, they are not meant for scientific computing. They are also interpreters, but you should not use them for computing. And if you know about MATLAB, IDL, or Mathematica, the difference is that they are not free. So here I'm going to give you a very short tutorial in all four languages at the same time. So what I suggest is that you connect to a cluster and look for either of these language or interpreters and choose one, and then try to follow along and type the small examples that I will show on the slides so that you get a feeling of how the syntax works and so on. And if you're not happy with one, you can switch to another in the process. So the first thing after you are connected is to use ML Spider to find out which modules are available for the interpreter that you want, and then use module load with maybe a specific release, and then Octave SciPy bundle. So the SciPy bundle is Python plus SciPy plus NumPy plus everything that is necessary for Python to become a full scientific language. And then when you have started the module, loaded the module, you can start the interpreter with running either Octave, Python, or Julia, all in lowercase. And you will have what we call a REPL, so a command line prompt where you will be able to type Octave or Python or R Julia commands. The first thing I want to show you is assignment. So how do we set a value to a variable? You see Octave in the upper left corner, R in the upper right corner, Python in the lower left corner, and Julia in the lower right corner. And you see that here with A equals 1 and B equals 2, I assign 1 to A and 2 to B. So if you type this, you will see that this is a double assignment. Two variables A and B are assigned distinct values. The same works exactly the same in Python. Sorry, it's a bit different in Python. You see that here I have one assignment here and one assignment here. In Python, I can have a dual assignment. So the pair AB is assigned 1, 2, and at the end, A equals 1, B equals 2. Okay, so it's, you will see that there are little differences in all the languages, but basically they can do everything that the others do. You see that in R, the assignment is not using the equal sign. So in nearly all the languages that I know of, programming languages, the assignment is using the equal sign. In R, they are a bit more fancy. It's an arrow-like sign. So this means assign 1 to A and assign 2 to B. And actually, you can reverse the arrow. It works also. And then at some point, they realize that the equal sign is a most universal, so you can actually also use the equal sign. And in Julia, it works like in Python. Okay, so if you type this in Julia and type A, you should see 1. If you type this in Octave and type A, you should see 1 as well. Okay, so the very basic introduction to a computing language is how to assign values to variables. Next, we can see basic operators. And I'm talking here about subtraction, multiplication, division, and exponentiation. You see here that I create a C variable where I assign an array. And the square brackets here are meant to create an array. You see that in R, it's a function that is used to create an array or a vector. It's called C for concatenate. So if you create this, you will have a vector with each element in the vector being the result of this operation. Okay, so the same here, each element in the vector is the result of this operation. In Python, as I mentioned earlier, Python is a generic language. So basically, to get access to the numerical or scientific part of Python, you need to import module. That is the name in Python. When you want to add functionalities from another piece of code, you import a module, and the module is called NumPy. And in Python, you can rename modules with the as command. And it's very, very often that in Python code, you will see this line, import NumPy as NP. It's a kind of standard or good practice to import NumPy as this. And then it gives you access to functions like this one, which creates an array with the contents. And here again, you see the same operators. You see that the operator for exponentiation here and here is the this one. And here is a double star. So there are small differences again, but basically at the end, you can do whatever you want with all of them. And you can see here the element-wise operator. So if I take C, which is my vector, and I multiply it with a dot star, I will have another vector of the same length, which with each element in the vector being the square of itself. So 1 is a square of this is a square of this, and so on. You see here in R, to get the same effect, you don't need a point. You don't need a dot here. In NumPy, again, no dot, and you get this. And here, you need the dot, and you get the same value here. So you see, syntax is a bit different, but again, in the end, it's the same. If you want to compute the dot product in Octave, it's simply the star. In R, it's the star, but surrounded by this % sign. In Python is the arrow-based sign. So this is the dot product of C by itself. And in Julia is the center dot. So this is actually not something that is on your keyboard. It's a center dot, the same one that you use when you write inclusive writing with in text. And in the Julia interpreter, what you do to achieve this, you type // C dot and then tab, and you will see that the C dot will be replaced with a central dot like this. And this is the vector product in Julia. Another very important things in all interpreted languages are sequences. You see that with 1:9 in Octave, I can create a sequence of the numbers from 1 to 9. And the colon is common to a lot of languages. In R, it works exactly the same. In Python, what you would typically use is a range or range from 1 to 10. You see the difference here. The upper bound is included. Here it's excluded. A little difference again, but you need to be aware of those differences when you switch from one language to another. You see here in Julia, again, you can use a colon to describe the sequence, but there's a small difference here in Julia that this does not create the sequence on the spot. What it does, it creates the definition of the sequence, but actually to get the sequence, you need to operate on it. And the simplest operations is collect. And if you call collect on the sequence, then you get the actual sequence. So this is more related to functional programming, as I was explaining, as I was mentioning in the session earlier. And this is what we call lazy evaluation. Actually, Julia will wait for the latest moment possible before transforming this notion of sequence into the actual sequence. And it allows you to actually work with infinite sequences. If you have at some point an infinite sequence that after a series of operations is shrunk to a finite sequence, in Julia you can do that simply because the infinite sequence is not evaluated. In Python, the equivalent are iterators. If you work with iterators rather than lists, you can work with the object that describes the list and not the list itself. Matrices are also an integral part of all these languages. So you can create one, for instance, with the reshape operation. Here you see in Octave, I run reshape, and then I give it a sequence, and then 3 and 3 are the 2 dimensions, number of lines, number of columns, and it creates me a matrix that is organized like this. You see all the elements from 1 to 9, 3 columns and 3 lines. In R, you see the same idea, the sequence, 2 dimensions, and the function is called array. But in the end, you get the same thing. Python, again, is the same idea. You use NumPy, use the range function from 1 to 10, and you get a sequence from 1 to 10. And here also, there's a reshape function. I give it 2 arguments, which are 2 dimensions, and I have a square matrix. You see the order here is a bit different. Julia works exactly the same with a reshape function that takes a sequence and 2 dimensions, and it changes the sequence into a matrix. If we speak about matrices, there are in all the languages functions to create empty matrices in a way. So with the zeros or with the ones, a function in Octave, you create a matrix that is all zeros or all ones. NumPy also has a zeros or ones functions. Julia, the same. In R, there is no 0 or 1s, but there's a generic matrix function where the first argument is the value that you want the matrix to be populated with. So matrix 0 creates a matrix of zeros, matrix 1, and then the 2 dimensions creates a matrix of 1s. When you have matrices, you can slice them. So slicing is the operation of taking a subpart of a matrix or of an array. You see this with parentheses is a way to extract the element on line 2, column 3 from the matrix. And if you replace one of the index with a colon, you get the whole line or column depending. So this gives me the first line. In R, you don't use parentheses, you use square brackets, but you get the same result. And you don't use colon, but you use an empty there's nothing there. It means a whole line. And if you don't give the first, then you get the first column. The syntax for NumPy is the same as for Octave, and for Julia is the same as for Octave Python. So slicing is a way to get the subpart of a matrix. Here is an example of slicing that takes one element every two elements. So here B is a vector created from the sequence from 1 to 9. And if I write it like this, 1 colon 2 colon end, it means give me the elements from the beginning to the end, but skip one element every, take only one out of two. So I have the whole 1, 3, 5, 7, 9 sequence. The complement to this is written like this. So start from 2 to the end minus 1. And again, the 2 between the two columns means only one every two. This is how you write it in Python. Again, you use columns, but they are used in a bit different way. But in the end, you do the same thing. In R, you need to use the sec command to create a sequence and use it to slice the other sequence. So R does not have the equivalent colon, but you can use a sec command in R to create a subsequence of the sequence and then use it to get access to the indices of the subsequence. In Julia, it's the same as in Octave. And again, you need to use a collect to get the actual sequence. Otherwise, you get just an object that describes the slicing of the sequence. More slicing, you can use operators to slice to find subparts of elements. So here with B, which is again a vector created from the sequence, I can compare that vector to a scalar, which is 5, and it gives me a vector of Boolean values that is false or 0 when this condition is not met, and 1 when it's met. So 1, 2, 3, 4, 5 are not strictly greater than 5, but 6, 7, 9, 8 are. So I get this vector. Here in Python, you see the same idea, except that rather than having 0, 1, you have explicitly false or true. R, again, as a vector of Boolean is printed as false or trues. While in Julia, you see that you need to use a dot to express that you are using an element-wise operation, and it gives you a vector of 0 or 1s, just like in Octave. If you want to find the indices where this condition is met, you can use the find command in Octave. So if I run find and then b greater than 5, it gives me the indices. So these are the indices, or no, these are the values that obey this condition in vector b. The equivalent in R is called which. In Julia, it's called find all, and in Python, it's called where. So it's one of the few areas where they all managed to find a different name for the function. They were creative, but basically they do the same thing at the end. Any questions until now? So I'm just giving you small building blocks for the language, and at the end I will offer you a small challenge where you will be able to use all these small bricks to create a solution to a problem, which I'm sure will be similar to a problem that you have to solve sometimes in your career. Loops, you know what a loop is. So you have the same operations that are done in sequence, one after another. In Octave, you use the for, so the for loops is used with for and then you use a colon to create a sequence. And then you use the end keyword to mark the end of the loop. And if you write something like this, I.I is so the index of the loop multiplied by itself, and it writes this as you would expect. The for loop in Python is written like this. So you see that there is no equivalent to the end in Python. So it's a specificity of the Python language that the indentation has a meaning, as a semantic meaning in Python. So as long as the commands here are preceded by the same number of spaces or tabs, they are all part of the loop. As soon as the function goes back to the first column, it marks the end of the loop. But in the end, with the range command, again, remember that the last upper bound is excluded in Python, while it's included in all the other languages, but you get the same output here. This is how you write it in R. It's more similar to what you would write in Java or in C or C++ with curly braces. So this is where the loop begins. This is where the loop ends. And in Julia, there's a for and an end command, keyword that mark the beginning and the end of the loop. And again, the iterator is based on a sequence. Conditioners. So I'm sure you're familiar with the concept of conditioners. The if statement exists in all languages. In Octave, you write if and then a condition, and the end of the block is marked with the end keyword. In R, it's with curly braces. In Python, is with the indentation, and in Julia is with the if and the end keyword. So it's consistent within the language. When they use curly braces for the conditioners, they use curly braces for the other control loops and so on. But they all have their specificities in how they write a loop. Here are elements on how to manipulate strings in all 4 languages. So if you have a character string that denotes an integer or a floating point, and you want to get the numerical object out of the string, in Octave you use str to double with a character string 10, and it gives you an integer 10. In R, it's as.numeric. That's a specificity of R. In virtually all languages, the dot is used to mark a sub-element of a larger item. So if you're writing in Python a class and you have an object and you have dot something, what you have after the dot is an element of the object. Here, it's just a replacement of a space. They would have preferred to write as space numeric, but then R would be confused as to what is a single operation or a distinct operation. So they use the dot here. So this is a single, as numeric is a single function. Again, you give it a string and you get at the end a number which is an actual number. So you realize that if you have a string that describes a number, you cannot add 5 to it, for instance. Well, in some languages, you can add the string 5 to the string 10, but you get 1 or 5. You don't get 15. If you want to get 15, you need to transform the string into an actual floating or integer element. In Python, you would use the float command that takes a string, gives you the number, and in Julia, it's a parse, and you decide which type the corresponding variable should have. If you want to print a number, which is the reverse operation from the number, you want to get a string that you can actually display, you can use format string in Octave or in R. Python has multiple ways to do that with a format string a la C like this, or with the most modern elements like this. And in Julia, you can use printf also with a format string. So this is how you create a string from a number. Glue is another way to write numbers, which is very similar to what we call a format, a F string in Python. All of these languages can manage special numbers, such as not the numbers, nans, or infinite numbers, inf. Some of them also have the notion of nothing or none. Nothing in Julia, none in Python, or null in R. And also R has the notion of NA, which is not available. So a missing value in R is depicted with the NA sign, which is different from not a number, different from the null value. Do you have any question about this? So just a catalog of small building bricks for all these languages. If you want a complete list, you can go to this website called Hyperpolyglot, and actually you will have a full table of all the equivalent of one construct in either language. So here you have MATLAB. So MATLAB is the commercial version of Octave. But you can see Octave as the free version of MATLAB. Here you have R, NumPy, so Python, and Julia. And actually, I put here the beginning of the page, but the page is kilometers long. Now, I would like to talk to you about graphical interfaces, because what you have seen are all commands or operations or functions that you write in an interpreter, but actually all of them have the graphical user interfaces. So Octave, when you start it locally on your machine, or if you're starting on a remote machine with an X forwarding, you get this graphical user interface where you have typically the interpreter, where you can write the commands that we've seen before. You have the workspace, which is the list of variables that are defined with their values. So you can actually inspect what are the values stored in the global variables in your workspace. And you have here list of files in the directory. So you can click on file, see the contents. You have an editor also here with a debugger. You see the dot here means, okay, run all this and stop here so I can inspect the values of the variables at this point in time. And there are ways to create graphics and plots and so on. The same exists for R. It's called RStudio, and RStudio is actually a distinct project from R. So you need to install RStudio specifically if you want to use RStudio, but the same features are available. You have a text editor, you have a way to inspect the values of the variables, you have ways to create plots, and you have the interpreter. All these you can organize in your workspace nicely. For Python, there are several equivalent projects, but the most used in scientific context is probably Spider. Offers the same functionalities, text editor, workspace inspection, plots, and so on. And in Julia, you have Juno, which is also a distinct project to the Julia language. So you need to install it by yourself. But in the end, you have, again, the same workspace notion with variables that you can inspect, a text editor, the interpreter, and a way to have plots written to the screen. These are the four graphical user interface you can use with the four interpreters. In R, furthermore, you can do what is called literate programming, which is a way to interleave text and computations. So if you typically run some program, you get some results, and then you go to LaTeX and you create a paper, you write a paper, and you have figures that you incorporate in your text. You can do both at the same time, and that's called literate programming. So you can have a single file that has both the text of your paper and the code that produces the figures and the results of the tables in your paper. And in Markdown, you can do that with Knitr or R Markdown. And you see Markdown here is the same Markdown as I was mentioning earlier before as a good way to write documentation. And actually, you can write complete papers in R Markdown where you interleave text and R code. And when you have written this, you can transform this into a web page where you see here the result of the comments that are here. The plots are included too, or you can create a PDF, or you can create another format that you want. You can even create a PowerPoint or a docx file, a Word file. The same exists, same ideas exist with Python. It's called the Jupyter Notebooks. So again, here it's a bit different. You don't write Markdown, but you have a website where you can write small pieces of Markdown into cells. And if you write Python into the cell, then the Python is interpreted. And so you can have the same here, a text file that describes a website where you have text and computations interleaved with the text. Notebooks exist in Julia as well. They are called Pluto.gl. And another thing that you can do in R is with Shiny create full websites that are based on R code. So with Shiny, you can have you have all what you need to create nice websites with sliders or other knobs that the user can use to modify values in the R code and have the graphs updated in real time or have the map updated in real time based on the input of the user and computation done in R in the background. You don't need to be a web developer to create that. You just need to learn how to use Shiny. And if you know R, then you are able to create a website where you can show off or demo your program, just letting the user play with knobs or any HTML input element that you can think of. The same exists for Python. It's called Mercury. And for Julia, it's called Interact.gl. You see that many extensions of Julia are called .gl, something. Talking about extensions, the nice thing about all those 4 languages is that they have a structure, an infrastructure dedicated to sharing code written in those languages. And these extra functionalities brought by extra code is called either packages or libraries or modules, depending on the language. But the ideas are all the same. In Octave, you have what we call an Octave Forge, where you have the list of packages that are available. And you can use the pkg install -forge and then the name of a package inside your Octave interpreter to have Octave automatically install and download that package for you to provide additional functionalities. The same exists in R. It's called the CRAN, the Comprehensive R Archive Network. Again, if you run install.packages in R and give it the name of a package, it will download the code of the package. If the package needs to be compiled, it will compile it for you, and then it will install it in your home directory where you can afterwards use it to write software that uses that package. Python has the PyPy, the Python package index, works exactly the same, except that you use the pip command in the bash interpreter, not inside the Python interpreter. But here you see pip install and then the name of a package, and it will download the package, install it in your home directory, and then after the package is installed, you can use the package with import in your code. Very easy. And finally, Julia is exactly the same. There's a list of packages that you can add to your Julia installation. What you need to know is that when you have a Julia interpreter, you need to press the closing brackets to enter the package interpreter, and so the prompt will change to pkg, and then you can use add and then the name of a package, and it will do what it needs to install that package in your home directory. Any question about that? No. the recent versions of all these interpreters are intelligent enough to realize that you don't have right access to global directories on the clusters, and so they will create private libraries for you and configure your interpreter to use those private libraries automatically. A few tips when you find that it's slow, because I said earlier at the beginning, if you remember, that one of the pros of compiled languages was the speed, and that speed was not the main feature of interpreted languages. But actually, the way you write code in the interpreted languages can have an impact on the speed. And here are some good practices specific to interpreted languages that you should follow. I will not go to details here because there are sections dedicated to Python and Julia and so on. So you can have a look there if you want. But basically, the most thing is avoid loops and use vectorized functions. So typically, if you have a vector of a large number of numbers and you want to compute the sine or the cosine of all the items in the vector, you should not write a loop that goes to over every element in the array. You should use the sine or cosine function from the language that itself is able to go through all elements in the array in its own code. And actually, that own code most of the time is written in a way that is very efficient, using parallelism if it can, and so on. All these languages allow you to link to fast libraries in C, C++, or Fortran. As I said earlier, if you remember, these were all created as wrappers for Fortran code. So actually, it's very easy to use already existing C or Fortran code into Python or R or Julia or Octave. And you should look into that if you have already a piece of code that works very fast in C. You don't need to create your own project in C. You can write the wrapping code in Python and just let C do the part which is actually compute intensive. There are some compilers or just-in-time compilers specific for each project that can also help you go from the interpreted world of Python or etc. into the compiled world of C. So there are compilers that create C code from Python code or C++ code from Julia code and so on. And then you can go parallel. Each of those languages have extensions that allow you to work on clusters with multiple nodes, with the exception of R. R is not really good at multi-node parallelism, and it's quite a nightmare to try to use multiple nodes at the same time with R on Sloan. I said at the very beginning that if you choose a language and you find a package in another language that you really want to use, it's not a problem. You can actually use bridges that allows you to create links between your code in Python, for instance, and a library in R. So here are all the pairwise different possibilities on using Python in R, you use this project. Using Octave in Python, you use this project, and so on. So you will never be stuck in the languages that you have chosen, because you can use bridges to other languages. And also, as I said earlier, use Fortran or any other compiled code into your Python or Octave or R code. So they are actually fast to learn and fast to code, because you're already in half an hour, you learned 4 languages, so they're very fast to learn. And they are fast to code in a way that it's easy. A lot of implementation details are hidden from you compared with the same program written in C or C++. Any questions about everything that I said until now?